for the recording. Great, welcome everybody to this week's GOCC. I guess before we get started, we want to do an invitation to attend this weekend's GSCC. So Galen, do you have a couple of words on that?
Yeah, the GSCC is an annual conference organized by graduate students for graduate students. This year we have, I believe, over 100 contributed talks and 3 keynote speakers. So there are like 6 parallel sessions. It's like a massive multi-person online conference, an MMOC. It's going to be a blast. If you haven't been to one before, this is a great time to sort of like see what they look like, because they're usually in person, and I'm suspecting next year it'll be in person again, so you can get a flavor of different sides of combinatorics.
And then I think we also will get to vote on who hosts the thing.
Yes,
So
there will
if you
be.
want to host, you should go.
Yeah. So usually how this, I should say something. I don't want to take up too much time, but I should just say next year I think it'll be held in San Diego because last year it was supposed to be held in San Diego and they canceled due to the COVID-19 pandemic. However, if you're interested in hosting in future years, I believe that we will have like a application process where anybody who's interested will just sort of like put their name into the hat, and then the Minnesota organizers will choose someone not for 2022, but for 2023. I think that's how this is going to work.
Awesome. So yeah, so if you're interested, please attend. Awesome. Okay, so I'll also remind us of the community statement. So we follow 3 guideline or guiding principles. The first one is we are all learning, and so the pandemic has forced us to learn in different ways. And so some of us know some of the material, or at least the background of some of the material that's presented. Some of us don't. So please make use of the chat, or make use of the chat, and then Alex or somebody will jump in and ask the question to the speaker. The second one is everyone has something to contribute. So everybody tackles combinatorics a little bit differently. And so there are connections and ideas, and we encourage you all to share them. And so please, again, use the chat. And then the last one is no one has all the answers, not even the speaker. And so if something stumps us, I'm sure we can figure it out together, or somebody might know the answer, or somebody that they can connect us to get an idea or an answer for. And with that, it's my pleasure to introduce Derek Hanely from the University of Kentucky, and he'll be talking to us about projective normality and Ehrhart Unimodality for weighted projective space simplices. That was a mouthful, but I think I got it right. So let's welcome Derek.
Thank you very much, Andres, for the kind introduction and getting through the tongue twister of this title. So in this talk, of course, we're going to be chatting about weighted projective space simplices and other ideas related to it. And I'm hoping that all the material is going to be well organized in terms of appropriate background before introducing new concepts. But I will forewarn that a lot of the theorems are very gross looking, and that they have a lot of formulas in them, but we'll kind of talk about the high level concept of what it is that they're trying to get after. So first, I'd just like to acknowledge that this is joint work with my advisor, Ben Braun, and also 3 of his former students, Rob Davis, Morgan Lane, and Liam Solis. So this is a relatively large project in terms of the number of people that were working on it. But to give us some sense of where it is that we're going, we'll start off with a little bit of background, just make sure that all of us are on the same page in terms of definitions and that sort of thing. And then I will introduce this notion, this set of simplices that we're going to be considering in the talk, referred to as weighted projective space simplices, kind of give you a sense of why it is that we're interested in studying these simplices, and then talk about the main results of our project. Okay, so to start, right, let's all, I know that there's been a lot of Polytope talks this semester, but I just want to make sure that we're all at least familiar with the basic definitions of them, right? So a convex polytope is a geometric object that can be defined in one of 2 different equivalent ways. The one way that we're going to be most interested in this talk is the V-type description or vertex description, in which we define a polytope as the convex hull of a finite set of points. Right, so we have a bunch of points in Euclidean space. We imagine, as Andres always says, you take a saran wrap, wrap them around the points, and then take all the points inside of that saran wrap, and that's going to define your polytope. Okay. Now there's an equivalent definition, which is referred to as a hyperplane or hyperspace description. This is where you define the polytope as an intersection of finitely many closed half spaces. Both of these are going to be equivalent, but I will state that verifying the equivalence between these two descriptions or going back and forth between the descriptions is a very, very non-trivial task. You may, like, I'll refer you to, say, like Ziegler's book, Introduction or Lectures on Polytopes. You'll learn about like Fourier-Motzkin elimination, things like this, in order to be able to convert between them. But another definition that's going to be important to us, because the class of polytopes we're going to be studying are lattice polytopes. Lattice polytope is just a polytope whose vertices happen to be integral points, right? They're points in the lattice Zn. So, for the sake of this talk, we're only going to be talking about lattice polytopes. Right, and let's just see a quick example, right? So here's an example in R2, two-dimensional lattice polytope, right? We see that it has 5 different edges and 5 vertices. So if we were talking about its V description, right, we could say that this is the convex hull of this set of points here, 0, 0, 1, 0, 2, 1, 1, 2, and 0, 2. Take the convex hull of that, and we get this sort of home plate shape thing here. But equivalently, we could also present an H description of this, which is the hyperplane description. If you take the intersection of all of these different inequalities here, that's also going to find this exact same thing. Okay, so in terms of these weighted projective space simplices, which we'll get to the definition of in just a few moments, there's going to be 2 important properties that we're going of lattice polytopes in general that we're going to be interested in. Okay, and the first of which is referred to as reflexivity. So a lattice polytope is said to be reflexive if possibly after some translation by an integer vector, it's going to contain the origin and its relative interior, and its so-called geometric dual, which is just the set of all points such that their inner product with every point in your polytope is going to be less than or equal to 1. That geometric dual is also going to be a lattice polytope. Okay, so this is what it means for a polytope to be reflexive. And then the other important property of interest that we're going to be looking at in this talk is that of the integer decomposition property. So a lattice polytope P is said to possess the integer decomposition property, or oftentimes we'll just say that it is IDP, if for every positive integer T and for any point that exists, or any integral point that exists in the teeth dilate of P. So here, this teeth dilate, that just means I take every point in my polytope and I multiply it by T and then take the convex hull of all those points. Okay, so if we look at, any positive dilate of the polytope, any integral point that's in them, we need to be able to identify some set of T integral points in the original polytope such that we can express this point in the dilate as a sum of those. Okay, so for those of you that are a little more familiar with these notions, if you say take this polytope and raise it to height 1, so take every point in the polytope, raise it to height 1 into the next dimension, and then take the polyhedral cone over that, this property would be equivalent to saying that every point, every integral point in the cone can be expressed as a sum of points that are in the level 1 slice of the cone. Okay, so so for this talk, right, we're interested in these 2 properties.
And Derek, just to make sure, the sum of those P's has to match, the number of those P's has to match the dilate.
The dilate, yes. Yep. Awesome. And of course, because we're also going to be assuming that our polytopes are reflexive. If you're reflexive, that after translation, that means that you're going to contain the origin, right? So some of these points could just be copies of the origin, but yes, you know, for integer decomposition property, it does need to be, well, we're saying that there does exist a sum of exactly t. You might not need t, you could need less than that, but there will exist some sum of t points in the original. Okay, any other questions about these two definitions before we proceed?
I guess
All right.
just generally, like, how
Yeah.
how restrictive are they as definitions? Is this like?
They're pretty restrictive. It will, so when you're just talking about like polytopes in general, the vast majority of them are not going to satisfy these properties. And reflexivity is definitely better understood to my knowledge than the integer decomposition property is. And in particular, the interplay between the two properties is also not well understood, because verifying that something possesses the integer decomposition property in general is extremely difficult. It's a super difficult open problem for general lattice polytopes in order to determine whether or not they're IDP. So I'd say that these are rather restrictive conditions, especially the IDP. It's quite rare among lattice polytopes.
Yeah, thanks. Yeah, that one definitely jumps out as being kind of like a weird definition. But I guess your explanation shows that it is kind of weird and hard to understand. And Galen's asking now.
And we'll see how weird it gets laler.
Yeah, so Galen's asking about a small example of an IDP polytope. Andreas has a suggestion of Reeves tetrahedron. I don't know if that's something that you're planning on showing later, or if it's like.
Yeah, I think Reeves tetrahedron works. I'll have an example of a weighted projective space simplex that's going to satisfy it later, because we have like a complete set of conditions for which to describe them. Yeah. Okay. Other questions? Okay. I'm realizing that. Okay, one second. Sorry. The way that I have this set up, the chat doesn't appear in my toolbar, and then the toolbar blocks my slides.
Yeah, I think that's pretty typical. Just don't worry about the chat, because sometimes people are like having conversation anyway. One of the organizers will tell you if something gets asked that's important. Very
good. Thank you. All right, so with that little bit of background, now I'd like to actually go into the definition of this, elusive object that I said that we're going to talk about that we haven't talked about yet. Okay, so what is a weighted projective space simplex? I guess first I should say what a simplex is. A simplex is sort of, so in a particular dimension, if you want a full dimensional polytope, so say you want a D-dimensional polytope, a simplex would consist of D+1 vertices, right? So in particular, if you take the convex hull of those, their affine span, it's going to be D-dimensional. Okay, so sort of like the smallest number of affinely independent points that you can have and still have like a full dimensional polytope in a particular space. So there's a special class of simplices that we're going to be interested in for the sake of this talk. These are weighted projective space simplices, and they're defined as such. So we start with an integer partition Q. Okay, so this is going to be some some vector of n positive entries. And we'll utilize the convention that we order these in a non-decreasing order. Okay, so we have like a unique means of expressing this Q vector. And the lattice simplex that's associated with Q is defined as the convex hull of the n standard basis vectors along with the negative of Q. Okay, and we denote this delta 1Q. So you'll hear me say delta 1Q a lot. That just means it's the weighted projective space simplex associated with our partition Q. Okay, we'll utilize script Q to denote the set of all lattice simplices that have this form. Okay, so any lattice simplex of the form where we take some integer partition and the negative of it, and all of the corresponding standard basis vectors take that convex hull. Okay. And why are these called weighted projective space simplices? Well, there's actually a nice connection to algebra here. The simplices that are in here actually correspond to a subset of simplices that define weighted projective spaces. And in particular, the vector where we append a 1 to the Q precisely gives you the weights that correspond to the projective coordinates for the associated weighted projective space. Okay, so a weighted projective space is essentially a toric variety, and we can talk about you know, a subset of these simplices are corresponding to these kinds of weighted projective spaces. Okay, I don't know too many of the details regarding its connection to the algebra, but these objects are useful because then we can use the geometric properties of these simplices in order to study open problems in algebra regarding these toric varieties. And furthermore, it can be shown that the normalized volume of these simplices is given by the total sum of the weights. So if you take one and you add together all of the entries in your Q vector, that's exactly going to be the normalized volume. So computing the volume of these simplices is quite straightforward. Okay. So that's the definition. And now I'd like to introduce a useful parameterization that we have for these delta 1 Qs in terms of the distinct entries that exist in the Q vector. Okay, so let's suppose that Q is, you know, Q1 through Qn, and we'll say that it has D different distinct entries in it. Okay, so that the D different distinct entries will represent with a different vector R consisting of R1 through RD, where again, we're going to utilize the convention that, you know, R1 is going to be less than or equal to R2, et cetera. Right, this is going to weakly increase. And then each of these distinct entries are going to have a corresponding multiplicity, which we'll just call X sub I. Okay, so we can equivalently represent our vector Q in terms of you know, this new vector where the exponents are just indicating the multiplicity of each of the different distinct entries. Okay, and the way that we'll re-represent Q is as this pair of the distinct entries vector and its corresponding multiplicity vector. And we'll say that both Q and the corresponding weighted projective space to that integer partition are going to be supported on the vector R with multiplicity X. Okay, so in this case, because there were D different distinct entries, we'll just say that our Q vector or the corresponding delta 1 Q is a D supported weighted projective space simplex. Okay. So before jumping into like various examples and talking about the properties associated with these weighted projective spaces, I just want to take a few moments to kind of motivate why it is that we care about studying these. And a lot of it comes from various open problems in algebra that have motivated problems in the study of Ehrhart theory. Okay, so I want to take a quick digression to kind of you know, introduce some basic Ehrhart theory concepts, and then we'll get back to the weighted projective space stuff. So if you attended Max's talk from 2 weeks ago, she gave a nice, pleasant introduction. I kind of want to reiterate some of the things that she stated here, and then we'll do a quick example. So the so-called Ehrhart function of a lattice polytope is the lattice point enumerator, which will denote I of our polytope in terms of some variable t, where that t is going to, or I mean, this enumerator corresponds to the total number of lattice points that are in the teeth dilate of P. Okay, and it's well known that that this lattice point enumerator is going to be a polynomial in the invariant T, whose degree will be less than the dimension of the polytope. Okay, and the corresponding, and with this lattice point enumerator, we can establish a corresponding generating function, an ordinary generating function, which we call the Ehrhart series, and that's the following rational function. So the Ehrhart series is going to be the ordinary generating function, where our coefficients on the teeth power of z are going to be, you know, the lattice point enumerator corresponding to the teeth dilate. And it can be shown that it can be expressed as this rational function, where the denominator is just 1 minus z raised to the dimension of the polytope plus 1. And the numerator is going to be, you know, this d degree polynomial in z. Okay. So Stanley proved that Stanley proved that all of these coefficients, these hk stars, can be are always going to be non-negative integers. And furthermore, we call this numerator the Ehrhart h star polynomial of P. Okay. So let's see a quick example for a particular polytope. Okay, so we'll take this simplex and R2, right, this triangle. If we take the second dilate of it, right, we're essentially just taking every point in P and multiplying it by 2. That's precisely going to yield this new triangle, which is 2P. If we were to take the third dilate, it would look like this. And of course, this pattern is going to continue for the fourth, fifth dilates, et cetera. Okay, so if we wanted to express our, our rational function in order to extract the Ehrhart H star polynomial, right, we need to figure out what the lattice point enumerator is. So if we consider, say, the 0th dilate of P, that's just going to be the origin that contains a single lattice point. We can look at the first dilate of P, the original polytope itself, right? This contains 3 different lattice points. We essentially add 2 to the new one. Whenever we do the second dilate, we're adding 3 new points to the 3 that were there from the previous dilate. And we'll see sort of that this trend is continuing. When we go to the fourth, we're adding 4 points, or when we go to the third, we add 4 points. If we go to the fourth, we're going to add 5 points, right? So essentially, the lattice point enumerator is going to correspond to a sum of consecutive integers, which we can easily recognize as a binomial coefficient, right? So in this particular case, the appropriate coefficient for the t power of z is going to be t plus 2 choose 2. And it's pretty straightforward to show that this ordinary generating function is going to be expressed as 1 over 1 minus z cubed. Okay, so what this tells us is that for this original triangle P, this polytope, our corresponding H star polynomial is just the constant polynomial 1. Okay, and ultimately what we're interested in is the various combinatorial interpretations of the coefficients of these H star polynomials, right? So for example, if you looked at the coefficient of the first power of z, that's always going to be the number of lattice points that are in your polytope minus the dimension plus 1. Okay, another thing, if you look at the coefficient of z to the d, that would be the number of interior lattice points in your polytope. So in other words, they can't be on the boundary. And there are other various interpretations of other coefficients. But the idea is that this polynomial is just recording combinatorial data about the polytope. Okay. So any questions about Ehrhart theory stuff before we jump back to our simplices of interest?
So maybe it's a coincidence with this, but when I see that H star equals 1, and then I knew, like you were talking about, you add 1 more point each time, is that true because of this, or is it just a coincidence?
So I think that's just a coincidence, because technically, right, when we do the next dilate, we're not just adding 1 more, but we're adding 1 more than the number of points that we added in the previous case.
Yeah. But,
right. So I feel like it's coincidental, but I also don't want to definitively say that and be wrong. But I mean, if we take a look at this, for example, so this should be corresponding to the number of lattice points that are contained in P. Well, we know P has 3 lattice points, and the dimension of the polytope here is 2. So if we take 3 and subtract 3, that's going to be 0, right? And the coefficient of z in this case is going to be 0. In fact, so the constant of this H star polynomial is always equal to 1. That can be shown. So I will now say that I think it's coincidental that we just have 1 here, because it's always 1 for any polytope, for any lattice polytope.
Thanks.
Yeah. Okay. Any other questions? All right. So now, getting back to why it is that we're, how is this motivated by the Ehrhart theory? Why do we care about these weighted projective space simplices? Well, because of the relationships to commutative algebra, we have these means of converting between algebraic objects. Oftentimes they're like these standard gridded rings. There's an associated polytope to them. And if we study the Ehrhart theory of that polytope, that tells us information whenever we translate back to the algebra land. So a lot of big questions are, what are the various geometric properties of these polytopes that are necessary and or sufficient for, say, the H star polynomial and to be symmetric, or unimodal. So unimodal means that the coefficients of the polynomial weakly increase up to a point, and then after that they weakly decrease. And a lot of these questions can sort of be surmised in the following conjecture, which is often attributed to Hebe and Ashugi, which says that if you have a lattice polytope P that's both reflexive and IDP, right? Remember our two important conditions from earlier, then the claim of the conjecture would be that P is going to have a unimodal H star polynomial. Okay, so this is still open. There's a lot of people that are working on it or have worked on projects related to it where you're trying to identify classes of polytopes that are reflexive and IDP and then study, the Ehrhart unimodality associated with those polytopes. But in general, as I was kind of alluding to earlier, the interplay between these three different properties, H star unimodality, reflexivity, and IDP, is very much not well understood. And it's primarily because determining whether or not a polytope is IDP is a very difficult problem in general. So the reason why we're interested in the weighted projective space simplices in this case, and why other people have studied other classes of simplices, is because they've been shown tonight to form a nice testing ground in which to generate examples that we can test the conjecture against. So, whenever we have these lattice simplices, we have a lot of combinatorial structure associated with them that we can try to leverage in order to determine whether or not these properties are satisfied. And that's exactly going to be what we're doing with these weighted projective space simplices. We have nice characterizations for when they're going to be reflexive and when they're going to be IDP. So I'd like to start with a result from Conrad's that gives us a complete classification of delta 1 Qs that are going to be reflexive. Okay, so one of our weighted projective space simplices is going to be reflexive if and only if we satisfy the condition that every one of the entries in our Q vector must divide the total sum of weights. In other words, 1 plus the sum of all of the entries. So if this isn't satisfied, you know immediately that that this simplex is not going to be reflexive. Okay, so here's an example. Suppose that our Q vector is 3, 4, 4. It's a three-dimensional vector, so we know that our corresponding weighted projective space simplex is going to be a three-dimensional polytope. So if we add up these entries, it's equal to 11. We add the additional 1, right, for that other projective coordinate. So that gives us a total sum of weights of 12. And 3 and 4, of course, both divide 12. Okay, so according to the theorem of Conrad's, we know that this polytope is going to be reflexive. And furthermore, using that support notion that we introduced above, this is going to be a two-supported polytope because we have two distinct entries inside of this vector here. Okay, and pictorially, this is what that polytope looks like in 3 space. And via this theorem, because we have this complete characterization, we've now identified an infinite family of simplices that are reflexive. So the next question that we ask ourselves in light of our motivating conjecture is, when are these polytopes going to be H star unimodal? When are they going to be IDP? When are they going to have the integer decomposition property? Okay. So this is, one important result that we'll be utilizing as we move forward. And the following is another important result that we'll be using. And, I'll admit that this looks very gross and I don't want us to read too much into it at the moment. I'll kind of explain what this means in terms of the geometry in just a moment. But in 2016, 3 of the authors on the current project had established a necessary and sufficient condition to determine when these the reflexive delta 1 Qs are also going to be IDP. Okay, and the idea, so just directing our attention here for just a moment. So if you look at the left-hand side of this inequality, what this is corresponding to, for those of you that are familiar with taking cones over polytopes and the fundamental parallelepiped, this is corresponding to the point in the fundamental parallelepiped, of the various points in our weighted projective space simplex. Okay, so we're trying to identify all of the various points in the fundamental parallelepiped that have height at least 2. And then the idea is we're going to find height 1 points in the fundamental parallelepiped. So we're trying to find a C such that the height of that is going to be equal to 1. That satisfies this set of non-linear equations, right? So we have all these 4 functions. All of these are considered over I running from 1 to m, where j is not equal to I. Okay, so for each j, we're trying to determine a height 1 point in the fundamental parallelepiped that is going to satisfy this system of nonlinear equations for every point that's height 2 or greater. That's sort of the idea. And while this seems very messy, the power of this theorem is that we can now determine whether or not these reflexive simplices are going to be IDP simply based in like elementary number theory, right? So we obtain a complete characterization of the reflexive simplices that satisfy the integer decomposition property that only relies on computing a bunch of 4 functions. Okay, so while the computations can be quite tedious, as the completion of the project, which we'll talk about a little later, is evident, it's nice in that it helps us like truly determine whether or not something is going to be IDP, which in general we said is a very difficult problem. Okay, so this is going to be a theorem that that we're going to make big use of. And a nice corollary of this theorem is that if one of our weighted projective space simplices satisfies both IDP and reflexivity, then we have this sort of criterion where the sum of 1 and then each of the entries in the Q vector modded out by any one of the particular entries is going to be equal to whatever that particular entry was that we're modding out by. And an equivalent statement of this theorem, if we rewrite it in terms of the distinct vector and its multiplicity vector, would be this. Okay, so what's the point of this corollary? Well, we say that if one of these simplices corresponding to Q satisfies one and hence both of these equations because they're equivalent, we'll give that a name. We'll say that that's the necessary condition for IDP. And the reason why we name that as such is because if Q satisfies this necessary condition, then it's automatically going to be reflexive. And a way that you can sort of see that is from this looks quite similar to what the characterization was in Conrad's theorem for the polytope itself to be reflexive. So if we assume the necessary condition, we get reflexivity for free is the idea. Okay. So at this point in time, I'd like to sort of give you a summary of all of the known results that we have about small supported delta 1 Qs, and then we'll move into the meat of what our current project was, which was trying to take these results and generalize them to the next case, the support 3 case. Okay, so at this point in time, there are complete classifications for the IDP reflexive delta 1 Qs that are supported on at most 2 distinct integers. So in the case that you're supported on exactly 1 distinct integer with some multiplicity, you're going to be IDP and reflexive if and only if your Q vector is just the all ones vector. And it's not too hard to convince yourself that you'd lose the reflexivity if these weren't all 1s, if they were all 2s or all 3s, because once you take that sum, that's of course going to be divisible by whatever the entry was. So if you have 2 and you take a sum of a bunch of 2s, that's divisible by 2. But when you add the additional 1 coming from that other projective coordinate, now it's no longer going to be divisible by 2. So we're not satisfying that condition from Conrad's theorem. Okay, so in the 1 support case, it's actually quite easy to identify all the IDP and reflexive delta 1 Qs because there's only 1 of them, right? The Q vector must be the all ones vector. But in 2016, Braun Davis and Solis had also established a complete characterization in the 2 supported case. So if your Q vector is 2 supported, then your corresponding simplex is going to be IDP and reflexive if and only if we're in one of the two following forms. You have a bunch of ones followed by a bunch of 1 plus whatever the multiplicity of the ones was. And in the second form, you're going to have 1 plus the multiplicity of the second distinct term for a number of times. And then the second term is going to be 1 plus x2 times x1. So these are the only two different possible forms that you can have. Otherwise, we will not be both IDP and reflexive. And in particular here, I'd like to note that in the first case, we can see that our first distinct entry of 1 is definitely going to divide the second distinct entry, 1 plus x1, trivially. But in 2, if we look at the first distinct entry, this 1 plus x2, that does not divide the second distinct entry. Okay, so this is sort of like 2 unique divisibility criteria for each of the different forms. And now we can finally move into the meat. Right, so we're going to extend these characterizations of IDP reflexive delta 1 Qs to the 3 supported case. Okay, and again, we have this nice messy theorem, right? But let me just kind of give you a summary of what it is that we're stating here. So we're taking a general 3 supported vector, the Q vector, and looking at the delta 1 Qs that satisfy the necessary condition for IDP. And the claim is that if we satisfy that necessary condition, then we have to be in one of the following 8 forms. Okay, so looking at the first couple forms here, if I look at my first distinct entry, that of course divides the second and the third distinct entries. And the second distinct entry in this case, the 1 plus x1, that's also going to divide the third one. So in this case, we have R1 divides R2 and R3, and R2 divides R3. If we move to the second one, our first distinct entry, 1 plus x2, that's not going to divide the second distinct entry, but it does divide the third distinct entry because it appears as a factor here. And similarly, the second distinct entry, the 1 plus x1 times 1 plus x2, that also appears as a factor in the third, so that's going to divide it here. Okay, so if you continue to look at the divisibility criteria for each of these, you'll see that this sort of gives us the 8 different possible divisibility patterns that we could find between those 3 distinct entries, right? R1, R2, and R3 dividing each other or not. Okay, but the big part of this theorem, the main claim is that the first 7 of these forms are going to be IDP delta 1 Qs, but the last form actually is not. Okay, so only these first 7 will give polytopes that are IDP, regardless of what our multiplicity vectors are, but the 8th one does not. Okay. So I just want to give a very like high-level overview of the idea of the way that this proof goes, with the caveat that the proof is like 20-some pages of tedious case analysis. But to begin, of course, we have to start by deriving the various forms. Sorry, someone was saying something.
Yeah, can I just ask a quick question before we get into the idea of the proof? When you came up with the statement of the theorem, like where did that come from? There's like 7 cases here, and I'm guessing that
it is. So when we're assuming that we have this necessary condition, because of that, we have that criterion that we can do this various divisibility with the distinct entries that are contained in the vectors. So essentially what it was we're like, okay, well, if we start with 3 arbitrary points, what inequalities must they satisfy in order to still have that necessary condition? And then with those inequalities, it produced, a number of cases in which the remainders fluctuate once you mod out by those different distinct entries. And with those remainder fluctuations, that actually will exactly give you those 8 different forms.
I see. So I should think of this as like there's some remainder statement that I'm not seeing, and if I look at like mod 8 or something, this tells me 8 cases.
Exactly. Yeah. So it was the deriving the cases part was actually the easy part. So doing the IDP verifications is where things become complicated. But I mean, that is an excellent question, and I kind of cheated and used this information that I used here in order to derive the forms. But this procedure was analogous to the procedure that Ben, Liam, and Rob had used whenever they did the 2 supported case. They had this condition that they knew had to be satisfied in order to be reflexive. So they used that to mod out by entries that gave a variety of inequalities that yielded only those 2 different forms that we had before. So in the 2 case, it was nice because we only had 2 possibilities. But now when we go to 3, we already have 8, but only 7 of them actually yield IDP things. Yeah, so so that derivation portion is the quote unquote easy part. And now comes the hard part, right, which is trying to prove the the IDP-ness of these different types of the delta 1 Qs on 3 support. Okay, so in terms of the 1 through 7, 3 of them were easy in that we could utilize some results known about affine free sum decompositions. So I don't want to get too deep into this. I'll at least state what the definition of this is. But the idea is you can take a delta 1Q simplex in some cases, and you can decompose them into smaller delta 1Qs of lower dimension. And if both of the lower dimension ones satisfy the reflexivity condition, then when you compose them to get the big delta 1Q back, that will also be reflexive. If both of the 2 smaller decomposed versions are H-star unimodal, then the composed version will be H-star unimodal, and that also works for IDP. Okay, so there were nice results that were established that if you satisfy any of those 3 conditions, if you can break up a big delta 1Q into smaller ones and prove those conditions are satisfied on each of the smaller ones, it's also going to be true for the bigger one. Okay, but what is the definition? If you take 2 different reflexive, weighted projective space simplices. So here, to make it more general, right, I'll have it in 2 different dimensions. And here we'll give labels to the first one, the delta 1P. The vertices are going to be V1 or V0 through Vm. The affine free sum for any I is just defined as the convex hull of the set of all points that are in the second simplex with a bunch of zeros appended on the end. And then you union the translated points by one of the vertices of the first one with a bunch of zeros appended on the left. Okay, so if you take the union of all of these different possibilities, the convex hull, that's the affine free sum. And the idea for types 1, 2, and 4 is that you can describe those as you can give affine free sum decompositions into smaller delta 1 Qs that are supported on 1 or 2. And because we know exactly which things are supported on 1 and 2 that satisfy IDP or reflexivity, then we get the IDP and reflexivity for free by that, theorem that I was kind of just generally stating earlier. Okay, so the idea here is for 3 of them, we just attribute it to other results that are known about affine free sum decompositions. But for the other remaining 4 that we have to prove for IDP, those do not arise as affine free sums, unfortunately. So we have to use some kind of direct means in order to determine whether or not they're satisfying the IDP condition. And in particular, the direct form that we used was that kind of gross looking theorem I presented earlier, where we wanted to find a solution to that system of nonlinear equations, that goofy 4-function thing. Okay, so this was like where the 20 pages came from, because unfortunately, all of these different types, because they're satisfying different divisibility criteria, we weren't able to employ the same techniques on all of them. There really was a unique approach to all 4 of these in terms of being able to reduce the 4 functions nicely to determine whether or not we could find a solution, and then we would find a solution, and that by that theorem would give the IDP. And then of course what remains is to show that that 8th form is not going to be IDP. So via that same theorem, we can essentially just show that there doesn't exist a C, right? So if we can't find a C that satisfies those nonlinear equations, then that's not IDP. So that's more or less how it goes. Yeah, I have pages and pages on a OneNote file of computing floor functions. Of course, the majority of that does not go into the paper. As you just say, it is straightforward to reduce the left-hand side of the equation to get this, even though it was, pages of work. But the nice thing is that all of it is just elementary number theory. So while the computations were tedious, it was doable. And we were able to establish, IDP for these various forms in the 3 supported case. Now, the idea is that we would want to also try to extend this to larger cases like the 4 supported or 5 supported. But just seeing the level of complexity change from when you go to the 2 supported, the possible forms that you have, that when you go to the 3 supported, the new forms that we have, it doesn't really seem practical to continue to use these sort of ad hoc methods where we're checking these, checking for solutions to these. So I highly doubt that we will continue in the sense of like looking at higher. There might be some other, criterion that you could identify to get IDP more generally, but obviously that's a very tough problem, which is why, we were just using this characterization theorem here. All right, and now, so at this point, right, according to that theorem that we stated above, we have 7 different forms that yield reflexive IDP delta 1 Qs in the 3 supported case. So in light of the original motivating conjecture that I gave earlier, the question is, are those also going to be H-star unimodal? Okay. So because that conjecture by Hebe and Nishugi said, if you're reflexive in IDP, then you're unimodal. That's the conjecture. Okay, so unlike in the general case for lattice polytopes, there's actually, again, a nice means that we can use the number theoretic properties of these simplices to identify an explicit formula for what the Ehrhart H-star polynomial is going to be. And in particular, for any delta 1Q, the formula is given by this. So we take this sum that goes from 0 up to the sum of all of the different coordinates in Q, and Z is raised to the power of this W thing, which we just defined to be B minus the sum of these floor functions, where we're taking each entry multiplied by B and dividing through by the total sum of the weights. Okay, so let's just do a quick example of this to sort of see where it's coming from. Again, we'll revisit that 2 supported reflexive polytope that we saw earlier, the 3, 4, 4. If you compute the WQ thing here, we're taking B and subtracting these 4 functions. 3 appears once, so we're going to have a 3 divided by 12. That was the total sum, so that reduces here to B over 4 in the floor function. And then because we have 4 twice, effectively, we're just going to get 2 copies of the same floor function, where if I plug in a 4 here for this QI and divide out by 12, of course, that's just going to reduce to 1/3. Okay, so this is our W. And if we raise Z to this for each of the B's that run from 0 up to the sum of the Q's, notice that there are going to be 1 plus the sum of the Q total things here. That's exactly going to give us this. Okay, so the number of times that Z has an exponent of 1 is going to be 5. Number of times that Z has an exponent of 2 is going to be 5. We can see here that this is symmetric and unimodal, right, which is nice. And why is it symmetric? Because there's also a result of Hebe's that says if you have a reflexive lattice polytope, then you can show that its H-star polynomial is symmetric. And we're getting unimodality here, which is consistent with the conjecture, and that this corresponding delta 1Q we said earlier is both IDP and reflexive. Okay, and also notice here, if you were to sum up these coefficients, that exactly gives you the total sum of the weights, right? 5 plus 5 plus 1 plus 1 is 12, which was this quantity plus 1, or a total sum of weights. Okay, so we have a complete, or we have an explicit formula for the H-star polynomial for a general delta 1Q. So a question that we'll ask before we tackle the 3 supported case is just, are delta 1Qs going to be H-star unimodal in general? Okay, and via a bunch of experimental results that were done in Sage Math, there appears to be a trend in the frequency of H-star unimodal delta 1Qs as the normalized volume of the polytopes grow. Okay, so here, this is a graph of a random sampling of integer partitions where we're computing all of the different delta 1Qs that have a particular normalized volume, and then looking at what proportion of those simplices are H-star unimodal. So as our normalized volume grows, we can see that there seems to be this downward trend. So at least experimentally, it's reasonable for us to conclude that H-star unimodality as the volume is growing is going to be rare. And furthermore, because we only have a small subset of delta 1 Qs in general that satisfy reflexivity and IDP, it's going to seem that the H-star unimodality is going to be even more uncommon among those. Okay, so there is a result for at least the smaller supported cases that if you're 1 or 2 supported in IDP and reflexive, you're guaranteed to be H-star unimodal. That's been established. We conjecture that this also holds for the 3 case. And it was easy for us to verify that it holds at least for the forms 1, 2, and 4, because we could just appeal to the affine free sum thing. Using the affine free sums, we could easily get H-star unimodality in these cases. But experimental evidence has also suggested that the other 4 cases will also be H-star unimodal, but without, it's not apparent to us how you would obtain that unimodality without applying various ad hoc arguments, kind of like what we had to do in the previous case where we were verifying the IDP-ness itself. So we did try this. We got very close, but there was one snippet for at least one of the forms. We're hoping that we'll be able to figure it out eventually to have completeness, but we do believe that all of these forms that are IDP and reflexive are going to be H-star unimodal. So theoretically, that is contributing evidence for the conjecture being in the affirmative. Okay, so that's everything that I had. Hopefully it was somewhat comprehensible, but thank you all for listening, and we'll open it up for questions, I guess.
Awesome, let's thank Derek. I have to get going, but Galen, thanks Derek for the talk, and Galen will chair the session now.
Great, thanks Andres.
And Galen has dibs on first question because it was on the chat a while ago.
Oh yeah, so just during your talk, Derek, I was curious, why are these weighted simplices you said they were a good testing ground for this conjecture, and I was curious if they're a good testing ground because you think you might find a counterexample there, or because they're easy to compute with, or?
Well, both. So certainly, right, if the conjecture isn't true, it would be nice to be able to identify a counterexample. I think a lot of the motivation of studying these simplices is just because of their relationship to the algebra stuff. So because a way that we could reform the conjecture that I stated earlier in terms of algebra is that if you have a Gorenstein domain, then its H vector is unimodal, right? So that's the analogous means of translating it into the algebra land. And so looking at the projective spaces, the weighted projective spaces, right, there's this obvious simplex that's associated with them. One reason why these are so nice is just because reflexivity is so easy to identify, right? All you're doing is just taking a sum of the entries and adding 1 and checking if everything divides it. So because you're taking a standard, or all of them are certainly going to contain the origin because you're taking the convex hull of the standard basis vectors along with some negative vector consisting of positive entries. But yeah, ultimately, a lot of it just boils down to having nice, concrete, combinatorial structure that we can work with. Yeah.
And, okay, one follow-up question, and then I promise I'll open up the real questions, which is that when you say Gorenstein, do you mean the Stanley Reisner ring of the associated?
Yeah,
Okay.
and because the translation of that in terms of the polytope is that its H-star vector is symmetric.
Okay.
Or so excuse me, the H-star, yeah, I mean the vector or the polynomial, right? The vector just being coefficients. So that the symmetry of the coefficients in your H-star polynomial translates to that the usual Gorenstein notion when you're in these standard graded rings or whatever.
Okay, cool.
That was definitely a real question, Galen.
Well, I like rings. I sometimes have a hard time with geometry or numbers, and then I think, oh, a ring, okay, I sort of know how to talk to it. Are there questions from other people?
So for the delta 1Q, have you found one that has Ehrhart unimodality but is not reflexive or doesn't have IDP?
I believe the answer to that is yes. Let me look at the paper for a second, because I think Ben wrote an example in here, but I just want to confirm whether or not that's actually true. Okay, I stand corrected. We have not. We haven't found any H-star unimodal that don't also satisfy reflexivity and unimodality.
So in that case, for the general supported case, is it possible that in order to find delta 1Q that has both reflexivity and IBT, you can just look for delta 1Q that have the Ehrhart unimodality?
That's possible. Yeah. I mean, that would. Yeah. So in other words, if the converse of the conjecture is true, then we could utilize that as a means of getting. That's true. Yeah. It's an excellent point. I'm not sure if it is. It'd be nice if it was. But again, there really is just no good understanding of the relationship between the three properties individually. Yeah, so it's kind of weird in that sense, but interesting nonetheless.
So I know sometimes when stuff satisfies unimodality, people are interested in log concavity also, which is like a strong condition. Do you know if there's any conjectures about that here, or it's only as strong as unimodality?
If there are, I'm not sure of them, because at least with my experience in reading papers in Ehrhart, like Ehrhart theory adjacent stuff, they only care about unimodality or symmetry, and that's it. And you get symmetry for free if your polytope is reflexive, right? So of course, if you're looking at more general classes that aren't reflexive, then that would still be something to check. But I haven't come across anything in terms of log concavity, or even what the consequences of that would be. Yeah. But that is an interesting question.
Yeah, this is like I think Alex is getting it. There's like, I don't know if it's a holy triple or something of, it's like unimodularity, log concavity, and real rootedness.
Right.
And somehow I feel like isn't there, and this is me thinking about something Andres said to me offhand years ago, maybe, that there's a connection between like unimodular triangulations and understanding some of these H-star polynomials. Is that something that we should be thinking about in the back of our head?
That is true. And earlier you were saying, hey, go to the GSCC, and during that I'm going to talk about finding unimodular triangulations in the two supported case. Yeah, so a reason why there's various results from like Bruns and Romer as well, that if you have unimodular triangulation, if you have a regular unimodular triangulation of a simplex, then it's going to be IDP. Yeah. Well, wait. There's maybe one other condition I'm missing there, but that's another means that people use in order to get IDP, just because in general it's so hard to find the appropriate points to add together. So oftentimes people are interested in triangulations of these polytopes as well, and that's what my other big project was on. And Liam is trying to convince me to look for a triangulation in the three supported case as well, but I don't know if I want to go down that road, because the IDP stuff was complicated enough as it was. Yeah.
Cool. Thank you. Are there other questions for the speaker?
So you gave a a formula for the H-star coefficients for these delta 1Q polytopes.
Yep.
I'm just wondering if there's any hope of using that to get, or if it's already been done to get some combinatorial interpretations for the H-star coefficients, like beyond what's the
beyond
few
the three standard ones. Yeah,
Yeah.
We have not, or at least, you know, I know that it hasn't been done, but that is an interesting question as well. Yeah, are there other combinatorial interpretations of other coefficients? That's a good question. I might think about that.
And then one more thing I was wondering is you were talking about how like the for support case would be ridiculous, but for the first step of it of finding the things that satisfy the necessary condition, is that sort of straightforward to do, or is that also difficult in that case?
I think it would be straightforward but tedious.
Yeah, straightforward but tedious.
And I agree. So I also think that you know, using that goofy nonlinear system of equations theorem, you could also prove it in the for case as well. But just because of the complicated nature of, I mean, let me just scroll up for just a second. So looking at one of these forms, I recall that 6 was the absolute worst because, I mean, like, so even just your first distinct entry, right? You have this term and it's also appearing as a coefficient on x2 that's added by 1. So now when you add on the layer that is one entry here, that you're now multiplying by any entry that goes over a range divided by some other particular entry, trying to reduce even just this floor function, you can do. Like if you try, like, ultimately what it came down to was repeated applications of the division algorithm and then factor out integral parts, leave the fractional parts that are left over inside. And ultimately, you know, you'll get that whatever floor function pieces you have left over, you just try to prove that they're either equal to 0 or -1. And then try to establish this equivalence. So like it would theoretically be possible, just utterly tedious. Yeah.
I guess I was curious about like is this the necessary condition, or this is the general, like
this is the general, you're going to be IDP if and only if you satisfy this stuff. Okay. Yeah, so the necessary condition was, no,
I guess I was wondering if the necessary condition would be relatively like straightforward to do, but then from there, like there's not.
Yeah, I think establishing a corresponding necessary condition in the for case, I think that wouldn't be too hard. But then using that to derive the various forms that are going to satisfy, you know, IDP, that again, I think it would be straightforward, but just really ugly.
Yeah, makes sense. Thanks.
Mm-hmm.
In the interest of time, I wanted to just say, you know, it's 1:10 almost, or it's 10 past the hour. So if anybody needs to scoot, I wanted to just sort of like pause here, thank the speaker one more time, turn off the recording, and let anyone go who needs to go. So let's thank Derek one last time, either with